So, good evening to all. Welcome to 8th week discussion for the NPTEL program for Machines 2 course. So, I am Sai Krishna Mulpuri and we'll be discussing electrical machines 2 concepts from the point where we left last week. So, the last week we were discussing about the induction machine, the power flow diagram in it, and what are all the losses that will occur in a machine while it's rotating, while it's stationary, and the no load losses we have discussed in detail. So today we will be discussing another important concept of, let me just share the screen. Another important concept that is starting of the three-phase induction machine. So that is a very important topic for any machine to because we all know when a machine was given supply, it will rotate and it will like produce the rotating magnetic field and all. But what happens exactly at the starting is a kind of important concept we need to understand, because starting is not any kind of uh, operation that we will just start the machine, it will start rotating and nothing different would happen, because it does happen, and we need to understand what exactly happens at the starting of the machine. So what happens, what type of current it will draw, and what effect that it will put on the other loads that the machine is drawing, and other kind of loads are supplying, so what effect it will directly relate to those loads, and that is a very important thing we need to understand. So we will be looking into all kinds of discussions related to starting of three-phase induction machine, and we'll also look into the methods which we will be employing as a starting methods of induction machine. So the purpose of starting methods also we will discuss, like why do we need these methods altogether. So I request students to mute themselves so to avoid any kind of disturbance. Thank you. So yeah, let's start. We'll be discussing the concept of now. We will take the equivalent circuit which we have derived the last couple of weeks, and we will see from that point what exactly happens in that when we start a motor, because it will be easy to relate. So what, when we give a supply to that equivalent circuit, that's again giving supply to the stator and current flows, that's the starting. So we will see the condition at that instant. So we'll be referring to a equivalent circuit. So stator side and rotor side we have these, and if we neglect the magnetizing branch, if the magnitude is such big enough, so we already discussed the equivalent impedance will be of the lower order terms, which is R1 and X1. So I'm just writing a approximate equivalent circuit just to understand the starting concept, the slip. And so this is the point where will be applying our voltage, input voltage. However, this is like a per phase equivalent circuit, right? So this is the input voltage per phase we will be giving to each phase of a winding in a machine. Now we are now interested to know what happens at the time of starting. Now we know the machine is stationary when we don't give any supply, so machine is stationary, and then we switched on the supply. Now we want to know how much current it is going to draw, so that's starting current, right? Since the machine is not yet started, and it when it starts to run suddenly, what is the important thing it will need to overcome? Because it's been standstill for a time and it has developed a term, a property called inertia, right? Inertia. Inertia is a tendency of a body to not to move from its point of position, right? When we are trying to forcefully move a body or a object, it has some inbuilt inertia in it, and it has to overcome that inertia in order to move or rotate. Now, since our machine is not started and we have given the supply and it has to run now, so due to it inertia, it is not yet started. So now it has to overcome that inertia in order to rotate. At that time, how much current it will draw. So due to inertia at the starting to overcome, how much current it means the machine. This is what we are interested in, how much current it will draw. Okay, and since starting, I know what is a slip at the starting. The value of the slip at the starting will be S is equals to 1. Right? Starting slip. So therefore, we are interested at S is equals to 1, and the instant when we gave the supply, the time instant, T is equals to just 0 plus. It's a transient condition when we just turn on the supply and we are interested to understand what exactly happens. So these two conditions, as at S equals to 1 and T is equals to 0, what happens? Now, since we know S is equals to 1, the R2 by S term will become R2 dash, R2 dash since S is equals to 1. And now, see, the reason I have neglected this because at the starting R1, X1, X2 dash and R2 dash, only when S is at some kind of slip like running slip, this R2 dash by S will be too high, right? So there will be some parallel branch as we discussed in the last week. So there will be resistance and there will be a reactance. So this is the core loss component. This is the magnetizing reactance, and this is the parallel branch with in parallel with the all the R1, X1, and X2 dash and R2 dash by S. So if R2 dash by is big enough, we can't neglect this parallel branch because this is also in the order of big and this is also big. So the parallel, both equivalent impedance, the resultant parallel impedance will be in the order of all these components because this is also a bigger one, this is also a bigger one. But right now, since at S is equals to 1, the impedance offered by this entire branch R2 by S will be R2, so it will be order of very low compared to XM. So that's why we kind of neglected this entire branch with RC and XM. So we kind of neglected this branch and we are taking the only simple approximate equivalent circuit. It's not a problem since because at the starting all these impedances are lower. That's why we have neglected the parallel branch. So now there goes my machine. I'm just writing it in the three phase now. A switch. I just want to write it in a show it in a way that where we are trying to switch on the machine. Let me just draw the winding first. The three phases. Now here, this is a line to line. This is not a per phase because this is a line voltage, right? This is a we are giving the rated voltage at this particular two phases, so it's a line to line voltage. And these are all the switches. Here also I am giving some voltage, and at the instant I will close this particular switch. So then only the machine will start, right? Now when you close this switch, current drawn will be very large, around usually what they say, the starting current when you just close the switch, the amount of current that it will draw will be 8 to 10 times the rated current. So let's say the rated current is 5 amps or 10 amps or something like that, then the full load current would like the starting current would be 8 times the rated current. If it is a 5 amps machine, it will draw 40 amps at the time of starting. So that much of high current, it is not good to pass such high current to the windings. So the question, what are we interested in? So will passing such high current is a bad thing? Is it a bad thing to flow such high currents to the winding? Because it's not that simple to say whether it's a good thing or bad thing, because it depends on the size of the machine and the inertia of the machine, and also for the time for which this huge current is flowing. Now that then only we can say whether it's a good thing or bad thing. We can't just say okay, this the current amount is big and we can't pass it through our winding. No, it's not that direct, but the parameters and factors it will depend upon is, let's say there is a huge current starting. So this will be depend upon the what is the size of your motor and inertia and also time duration. This is the time duration for which this huge current will be flowing. Okay. So these are the three parameters which we can, but if we know, then only we can say whether it's a good or bad. So it even now to have a more clarity on it, let's say let's take a example situation where we have a motor with a 10 amps rated condition, like 10 amps, uh, like rated current. I can say 10 rating of the machine is 10 amps. That is the rated current is 10 amps. So 10 amps is the rated. So then at the starting, it will it will take around 8 to 10 times. So I'm taking 8 times 80 amps at the starting. Now this 80 amps will flow through the motor. At this condition, let's say we have two motors, which is a small motor. Small motor is the rating is less. Uh, Another motor is big motor. It is having a bigger ratings. So if the motor is very small and if the motor is very big, we are trying to pass 80 amps through both the motors. So can you say which motor? Can you say which case is better, to pass the 80 amps through the small motor or to pass the 80 amps through the big motor? Which is good? So here, the thing which we have to understand is, as I said, the size of the motor, inertia of the motor, the time duration for which this huge current of 80 amps will be flowing. So here, it is good for this 80 amps to flow through the small motor. Why? Because if your motor is very small and you have given the full voltage, that is the rated voltage of that particular motor, and there is a starting torque is there, and if it's a small motor, the inertia would be lesser. Small motor because inertia would be less. So therefore the machine will pick up the speed very fast. So that's what I want to tell. Now because since is the motor is small, Small motor, less inertia. So because of this less inertia, the motor will pick up its speed very fast. Now this, even the 80 amps is being passed to the small motor. As the time passes, it will pick up the speed slowly. The slip will start to rise. See, initially the slip is 1 at the starting. So as it's become as it is rotating, your slip will change. And then your motor is picking up speed, and it is rises very rapidly. Okay, now this takes 80 amps, but the time duration for which it is taking is very brief period, because it has to overcome very small amount of inertia, and it can bring up the speed very quickly and rapidly. So it's a very brief period of time your current is being flowing this much high current. And we know, to spoil a winding in a machine, or to get the winding of the machine damaged, you had you have to pass this amount of large current for considerably enough time, such that your I square RT losses, the time for which your I square R losses will be much more, and the heat would be generated. So if your inertia is small, your 80 amps will flow for a very brief period, and it's okay, because since the current will go down as your slip gets to pick up. And see, now 80 amps is initial current, and your slip is picking up, your slip is changing, and then your R2 by S term. So this will be going increasing, and then your R2 by S is increasing. So this will increase, and R2 by impedance is increasing, means what? Your current will go down fast. So this will 80 will be going down. So now if the motor is large, very large, you mean the larger diameter of the motor, small motor and large motor. Now if you pass the same current in the large motor, it has a larger kilowatt rating. Now say, let's say, this high current, let's say it is rating itself is, let's say, 50 amps around rating. Now at the starting 8 times it, let's say 400 amps, it is passing to the motor itself windings. Now this kind of larger machines have larger inertia, and when it has larger inertia, it means it will slowly start rotating at the starting. So gradually the speed will rise. There is no rapid rise in the speed. So now this condition of S is equals to 1, where at the starting this condition still prevails for a longer time. Now the current decrease will be there. The current does decrease, but it will go down very slowly. So this will eventually spoil your winding, because 400 amps of current is flowing through your winding for a large time, and it will spoil your winding. So spoil winding means what you will see, like usually there will be a smoke coming from the winding. There is a small kind of fire you can see in the winding. So that the cause of one of the reason that could be having is this condition, when it is the high current is flowing through the starting and your winding gets damaged, because you are allowing that high amount of current flowing through your windings of the machine for a considerably longer time. That is not at all an ideal case. So that is, if you see from the motor point of view. If you look from the source point of view, okay, if your source is capable of supplying that much burst of high current, there also there is some problem. We have seen from the motor side what the problem is. Now from the source side, if you see the problem of giving that burst of high current for a brief period of time, there is also a problem there. So that is like another issue related to source side. If it's a bus connected system, now your supply is connected to different loads that you see, right? That's how in your house also it happens. Like you have your main supply, three-phase supply or single phase supply. Now for that supply itself, you have all the loads in your house. You have your tube lights, you have your grinders, and you have your refrigerators, air conditioners, TV, everything will be there. In such a case, if one of the component is drawing this much amount of current at the starting, the supply has to provide that. So there is no other way to get that much amount of current. Your supply has to provide it. So what happens in that case? So let's see, it's in a bus kind of system, that is in that single bus producing like providing for different loads. Let's say this is three phase A, B, C. This is the bus. Now, this switches are for our motor. Okay. In between this only, we will have all the loads. So these are all the loads, consumer loads, which we are consuming in our household. Let's say. So after these switches, we will have our machine. Now, the instant we are closing this switch, right, there will something will happen where your incoming supply, this bus is supplying to all these loads also and your motor also. So when this large current is drawn, let me just even draw it like a. So I'm modeling our source as a some source with a impedance. Okay. So these are all the switches we have. This is our machine, and this is the stator part, and we have the rotor here. Okay, and this could be of any other load, like maybe it's a refrigerator or something else we have here. And between the switches and this we have our loads here. All the tube lights, mixie grinders, everything, a TV, everything we have here. And now at the starting, when just we close the switch, and this is the part where your series current will be flowing through this series impedance, source impedance, and it will go through this your requirement load, and this is where the current will pass. Now at the start there will be a burst of current, right? There is a high amount of current, large current will flow. Now this large current will be passing through this all impedances, right? So there will be a huge voltage drop here itself, right? There is some bus voltage, constant voltage, that is always constant. Bus voltage cannot change. Now at this point you have some big constant voltage, and now this at ABC point you have some voltage which you are supposed to get have a constant voltage, that is a stabilized voltage, and then you will have the same voltage given to one of the loads. So this all loads are connected parallelly, and you are expecting after this drop I will have some less than V current, maybe V minus some VD, that is a drop across these impedances, and you have the V minus VD across this point ABC. Now at the starting, one of your load, which is this one, is drawing a huge amount of current that has to come from here, and the huge current is flowing through these impedances, and this drop combined with this huge amount of current will be higher. Because of this higher drop, this VD will be much more. So this, due to this large current, voltage drop across your source impedance ZS increases, and that will, what happens, the voltage at ABC, this point will reduce, V minus larger drop, and this will reduce. So with this reduction in the voltage, you will see a voltage dip in the supply, in the input voltage to our appliances. So every time you switch on this switch off induction machine at points ABC, whether like where other consumers are also connected, we will see a dip in the voltage. So this you also might have observed in your household. So whenever you are switching the refrigerator, or whenever you are turning on the AC air conditioner, for a brief period, you can see a dip in your tube lights. So that's the exact reason why this is happening, because at that starting moment, your air conditioner or your refrigerator is drawing huge amount of current, reducing the input supply to the appliances. So that's why it happened, but it is very for a brief moment of time, because till your motor picks up with you inside your air conditioner, the dip will appear, but very small instant of time. So yeah, now if you see uh, this, let's say with respect to time, if you are seeing this dip, so this is the voltage at the ABC at the supply of the consumer, so it is having a constant voltage, but at this instant you have turned on the switch on, and then you will see a dip in the voltage, and once the motor picks up the speed, it will come back to its position. So for this brief period of time, let's say this delta t period, you saw a dip. This is okay if its delta t is very small. It's not much of a problem. We just saw a dip and it's back to working again. What if it's a bigger motor? This is for a small motor. But the same case, if it's for a bigger motor, we just saw for a bigger motor, the inertia will be much more, and this starting current will flow through this bigger motor for a considerably more time. So then the same instant, if you want to see here, you have switch on, and the dip will be much more, like it will take much more time to come back to its normal phase. Dip will be bigger, and this is for a bigger motor, and this is the voltage at ABC. So what I'm saying is, for a bigger motor, the dip is very large, and for considerable amount of time, your lights will go low. So that will make the users and the consumers uncomfortable, right? So we just saw two problems at the motor side as well as the source side. So if it's a motor side, small or big motor, that's the issue. Those are the two problems. I'm writing it here. One is motor side, small or big motor. That is the issue. And the source side, the issue is it will affect the other consumers, other loads, right? So these are the two issues which we have seen at the starting of your induction machine. So this we might have observed in households, and also like whenever supplies is there, we will see a little fluctuation in the lights and appliances, and then they get back to its own intensity. So, but this on off, if we are doing it rapidly, we are turning on the AC and then we are turning off and then we are turning it off, it causes very discomfort whenever your lights goes dim like that. So that's okay, it's only causes us a kind of discomfort, it's okay. But what about some critical equipment, like let's say we are in a hospital, all loads are connected to particular supply, and whenever we are turning on a critical equipment, your dip in voltages can't be allowed. So because you are supplying some life critical appliances to health and medical reasons, you can't encourage this kind of dips in hospitals. These are very critical situations. So there you can't encourage this kind of dips. So some because some loads may need on and off, like critically, where you have to turn on the machine. So but you can't encourage these dips. And like in some rice mills also, some there will be some loads that we need to on and off continuously, but that should not stop the process of other machines. So yeah, in these conditions, that's how the need for going for this starting methods has risen. So after looking at these problems from the source side and motor side, people thought that okay, we can't avoid anything. We can't avoid turning on, turning off, because sometimes it is a need, and we can't also allow for this dip in the appliances. That's also discomfort. So then people thought of going for these starting methods. Now, the obvious solution, what you can think, like initially, if you want to reduce the big current, the obvious solution which one can think of is reducing the voltage, right? Like in the starting, you are giving the rated voltage, full per phase voltage. If you go back to the uh, previous, see this particular machine, so we are giving the rated voltage line to line to the initially. That's why it is drawing the rated current, and the rated current will be 8 times of starting current will be 8 times of it. So simple solution would be, anyone would go for, like, let's okay, at the starting, let's give a reduced voltage. We will allow the motor to pick up the speed, and then we will shift the input voltage to the full rated voltage. So that's obvious solution. So that is one of the solution, that is reduced voltage starting. Okay. Now one more solution, which is not much solution we can say, but it is a, like we already discussed, for a small motors there is no need. So there is, even if you give full voltage, you can apply the full voltage, because for small motors it will only be for a brief period of time. So such method is called direct online, DOL, that is direct online starting. See, this is not a very some good solution. It's like direct online starting method. It's only for a small motors. Why? Because for small motors, you can apply the full voltage. Can be applied. So one is a full voltage method, where even if you apply full voltage, there is no loss in it, and the other one is the reduced voltage starting. So within this reduced voltage starting, we have different methods. That is reactor starting, auto transformer starting, and another method is also there, like star delta starting. We will also discuss that today. But the main methods are DOL, reactor, and auto transformer. So within this, DOL is the full voltage starting method, where the reactor starting and the auto transformer starting are the reduced voltage. So yeah, that's simple trick, right? If you reduce the voltage at the input during the starting, it will not draw that much of 8 times the rated current, but it will draw 8 times the input current, but it will just go down drastically if your input voltage is not full voltage. So that's okay. But one condition is that if you remember the previous week's discussion, when you are trying to insert resistances in the rotor circuit, right? We introduced external resistances in the rotor circuit and we saw an increase in the starting torque is improved. So I hope you all remember that discussion. I'm just drawing this is torque and this is slip. So we have seen if this is the maximum torque and this is s is equals to 1, s is equals to 0, and we started here, and this is the maximum torque and this is this starting torque, right? TST. So this is, let's say this is for R2, and we have increased the external resistance and we got, so this is for R2 plus R external. You remember, I guess this is R2 plus 2 times R external. So TST2, TST3, you are getting an improved starting torque if you are going for an increased resistances. So at the starting, you can just increase this increase resistances, because R2 by S, the total resistance R2 plus R external dash by S. This is the total impedance. So if you just add, like for a slip ring induction where the rotor terminals are available for you, just by introducing external resistances, total impedance you are increasing. That means the starting current will go down and starting torque also improving. So you don't need any starting methods separately for this kind of slip ring where you can just introduce the R external. But these methods of starting methods are for such motors where the rotor terminals are not available for you. Usually we have squirrel cage induction motor, right? There's a squirrel cage caged on the rotor side. You can't access the rotor terminals. So in that case, you can't insert external resistances. So all the starting methods are for cage rotor machines. That is, rotor terminals are not available, right? If rotor terminals available, like for the slip ring or wound rotor, you can just insert external resistances that will limit the starting current, because impedance will go up, even starting torque also will improve. Now we will see all these three starting methods. In fact, four we will see, that star delta also. Fourth one we will see later, and then we will compare these starting methods with the DOL starting, because in DOL starting, you will know what is the starting current. That will actual, if there is no starting method, it's the DOL starting, direct online starting. So in that we will see what are the starting currents and what are the starting torques, and we will compare it with the rest of the three methods, that is reactor, auto transformer, and also the star delta starting. So let's first discuss the standard method, that is DOL starting. Now see, we are always drawing stator as this kind of star, right? Even if you see the previous diagrams where I given the supply, see the stator is a star here, again a star here, also I have drawn star. It's not mandatory that all stators will be in the star only. The stator could be in the delta also, like this kind of delta connected stator will also be there. But the reason we will go for star is it's simple to represent it, simple connections and all. But usually stator can be delta as well. So ultimately we need balanced three-phase current flowing through the winding. So it doesn't matter the kind of connection. You need a three-phase balanced current flowing through your windings of the machine. So, but for the all the starting methods, I'm going to be making assuming the stator as a delta instead of star, because the fourth method which I told you, which is the star delta starter, we need to compare all the starting methods, right? So we have to make follow a standard convention. That's why I'm taking the rotor as a star delta, because for the star delta starting, the stator needs to be delta. That's the mandatory thing for it. So to have the same convention for all the methods, I'm kind of following the assuming the stator for the starting methods to be a delta one. Okay. Now, because star delta only is possible if your machine is delta connected. That's why. Okay. Now, dual starting. Let's see. So this is our machine and delta connected stator. Now here we are applying the rated. In dual, you have to remember we are giving the rated voltage directly line to line supply. Okay. Now here we have our rotor. You can't access this rotor. This is a cage rotor, and this is your stator. Okay. Now at starting, S is equals to 1, right? And we have applied V rated, right? Now we estimate what is the starting current drawn by the machine and what is the starting torque that is being developed in the machine. Now, from the equivalent circuit, we already saw at the starting the impedance offered by the circuit is very less. Now, this particular so this entire impedance at the starting will be offered will be very less. So here we are, even though we are applying the V rated here, that is line to line, your current that is flowing in the starting will be dependent on the uh, starting method, and also here the impedances are very less. So impedance will be less. And one more thing you have to observe is this is a per phase. This is a per phase equivalent circuit. And here the voltage which I am giving is the line voltage. Usually in a delta connected system, line voltage will be equal to the phase voltage. That we know that for a delta connected system, line voltage is equal to phase voltage. So this is also equal to V phase, and this is also equal to line. Okay. Now we are interested. The goal is to calculate the starting current. Now here we have this, drawing it again, machine. Okay, and here we have the I'm interested. So in all cases we need to calculate how much starting current it is drawing from the supply, right? That is the goal. That is the goal. So this is supply. So here I am giving the rated line to line, and this is the starting current drawn by the line, right? But This is the current that is flowing through the windings. I will write this as I starting current drawn by the winding, or you can say this is the phase starting current, because this is a line current and some current will like flow through this winding. That is the winding starting current or a phase current. Now you see, you have your equivalent circuit here, and you have given some voltage which is equals to phase rated here, and this impedance is, let's say the total source impedance, like the phase impedance is some Z, and you are trying to calculate the starting current flowing through your winding, which is phase is equals to, now we have applied a rated voltage, rated, divided by this Z. So it is like a, if you see the, the same transfer, the same equivalent circuit, it is same for the transformer. When you we discussed this condition, the induction machine is just like a transformer when its secondary is short circuited, right? So it's like a total short circuit impedance. Usually people call it this, Z is a ZSC. You have short circuited and there is a resistance now. This entire impedance is ZSC. Now your total starting current would be equal to this voltage divided by the entire short circuit impedance. Now this is exactly the starting current drawn by your winding in the direct online. Now what will be the IST of line in your direct online starting? So your line current will be in a delta connected system. It will be root 3 times the phase current. That's the winding, right? Now it will be root 3 times V rated divided by ZSC. Now you know how much is the starting current in the DOL method. This is the starting. Now next one we are interested to calculate is the starting torque. So for every method we will see the starting current, starting torque, and we will compare it with the direct online. Now how can you get the starting torque? What is the formula for it? In the previous 2 weeks before last week we discussed the formulas. So if you remember, your starting torque will be equal to air gap power by 2 pi ns. It is also air gap power if it's in synchronous watts, but it will be PhE by 2 pi ns, it will be a Newton meter. Right. Now we know the air gap power formula, 1 by 2 pi ns if you take common. PhE will be 3 I square R for the 3 phase. 3 times, what is the current flowing through it is winding will be, rotor winding, that is I starting winding, IST winding square multiplied by R2 dash by S, that is referred to your stator side resistance. However, this S is equals to 1 here, since it's a starting current and S is equals to 1. You don't need to take the S part. Your R2 dash will be there and your I started winding will be there. So I am writing directly the starting torque in the DOL method would be 1 by 2 pi ns 3. I'm substituting I start winding, which is equals to V rated by ZSC whole square multiplied by R2 dash. So this is the starting torque in the DOL method. Now we got the both starting current and the starting torque. Now let's see the rest of the starting methods, and it will be interesting to see how much amount of starting current we are reducing in every starting method. How are we achieving it? how the reduced amount of voltage input we are achieving in the first place, and how that reduced voltage is resulting in a reduced current flowing through the windings. Now, the first method of the reduced voltage will be reactor starting. Now, see, after supply, the name itself says that we are kind of using a reactor. Now, this reactor will actually have some turns ratio, and it will reduce the input supply. That's how we are achieving the reactor. There is a reactor box you need to buy first, and you need to place that reactor between the supply and your motor. So then you will have some reduced voltage input to your uh, motor. So that's how you will achieve it. So you will see this in a figure now. Supply will be there, like that's common. You are not changing anything in the supply. You need to supply rated voltage. Now, since the range is reduced voltage, this entire rated will not go to the machine. Your machine is here. Machine is here, but in between rated and your machine, you are kind of placing a reactor. Now see, this whole reactor is varied. Now here, if you have uh, some reactor, this voltage across the winding will not be rated voltage because of this particular reactor. Now see, this is some V rated, and the voltage at this point will not be V rated, because I mean this particular point, this point it is V rated, but this point and this point it will not be V rated. It will be some X times V rated. X will be factor line to line. This X is a factor that will be between 0 to 1. There is a part of the input voltage you are applying across the windings of your machine. So again, you will have some starting torque here. This is the starting torque, starting current, the line current, because of this reactor, right? And then you will have some X voltage applied here, and again there will be a starting current flowing in the winding because of the reactor. So now we are interested in calculating this starting current, how much your winding is taking now. Previously it is taking some X amount of current in the DOL starting now. Because of this reactor, we will see how much, of course you will have some rotor here, that is caged rotor, and you will rotate it, and you will see now how much starting current your windings are taking in this case. Now let's say now our goal is to calculate this particular starting torque, how much your machine is drawing from the line, right? So your IST line, because of the reactor starting will be, see, it's a delta. It will be root 3 times of the phase, that is I starting, reactor, winding, and again it's the voltage across the winding divided by the impedance. Now the interesting thing is the voltage is not V rated, but it's a X times the V rated. reduced voltage. Impedance remains same. We have not changed any impedance here, but the voltage is being reduced. So this is the starting current in the reduced voltage starting. Now, if you see the starting torque in the reactor starting, PAG by 2 pi ns. This will be 1 by 2 pi ns if you bring out 3 I square R and 3 IST reactor square, that is flowing through the winding, and your R2 dash by S will be 1. And if you substitute it 1 by 2 pi ns 3 times X times V rated divided by ZSC whole square multiplied by R2 dash. So this is the starting torque in your reactor. There is nothing difference. You have got an X term. In the current you have an X term. In the torque term you have an X square term extra. Okay. Now let's compare both. In the it's DOL and the reactor. In the DOL, your starting current drawn by the machine is equals to root 3 times V rated by ZSC, and starting torque in the DOL is equals to 1 by 2 pi ns 3 times of V rated by ZSC whole square R2 dash. Now in the reactor starting, we have root 3 times X times V rated by ZSC, and the starting torque, okay, there is no line at all, will be 1 by 2 pi ns 3 times X times V rated by ZSC whole square R2 dash. Now let's take a ratio of these currents and the torques. I starting, I am taking the ratio of currents in both reactor to DOL. So if you take these two and you will be left with the X, and if you take the torque ratios, it will be X square. These are very important relations which we are very simple to understand but useful for your problems. So this, what does this ratio actually mean physically when you include a reactance base starting? It will say that your starting current in the reactor base starting, it will be reduced by X times, and your starting torque will be reduced by square of x square times. So whatever current you are drawing, you are able to manage to reduce it by x times. X here is the tapping and the ratio of the reactor at which you are running it. Now if you can vary 0.8, 0.9, 0.5%, 0.4%, 50%, 40%, if you keep the tap ratio accordingly, your starting current as well as your starting torque will also be getting reduced. Now let's see the other starting error, which is the auto transformer starting. That also kind of reduces, but the factor will be different. You will get even more reduced current in the auto transformer. It is actually even better method than reactor because it reduces starting current even a bit more. That we will see now. What is the amount? You know the if you know the functioning of the auto transformer, it will be easy to understand. So okay, again we have supply and we have our machine here, and rotor, cage rotor. Okay. Now between this two supply and also this our machine, we are planning to introduce an auto transformer. Auto transformer will have a primary winding and secondary will be taps, right? So the three-phase auto transformer, I'm drawing it and I'm connecting it to the supply. Now here you will have the rated voltage that we are giving to the input of this auto transformer. But this auto transformer will secondary will be connected to our machine. For every winding, we are taking the tapping. Now see, so this is the supply side. Now this is whatever the current that is drawing from the supply. The auto transformer is taking in. This is the starting current that is lying by the supply. And now here is the starting current, line current by the machine. Auto transformer by the machine. And here it is V rated. And here of course you will have the X times the V rated applied across your windings of the machine. And the current flowing through this would be I starting, line current, sorry, phase current, right? I starting, winding current due to this auto transformer starting. Okay. Now we are interested in calculating the starting currents. This is the voltage rated line to line we have given. And now the goal is to calculate the starting current drawn by the supply. And now let's see the I starting current drawn by your winding due to auto transformer starting. That is again the X times the V rated divided by ZSC. That's again the same because the voltage is V rated and the impedance is Z. Now, what is the starting current, that is line current drawn by the machine? I am talking about this particular current. It will be root 3 times the phase current. So it will be root 3 times X V rated by short circuit. Now our goal is to calculate the input supply, right? The line current supplied by the supply. Now in a transformer, what is the condition? How to calculate this current? Primary current. In a transformer, input kVA will always be equal to output kVA. Transformer kVA is very constant. You can't change it. 5 kVA transformer is 5 kVA in input and output. You need to calculate voltage and current in the input, voltage current in the output. You will have the same kVA. Only your power levels will be, voltage levels will be go up, step up and step down, but your kVA ratings remain same. Now with this relation, if I calculate the input kVA is root 3 V line I line. So root 3 times input is rated supply line to line. The current would be this current line IST supply. That's what we are interested to calculate. Is equals to output kVA. This side. So this is root 3 times the voltage is x times kV rated line to line, and the current would be line drawn by the machine. That is the auto transformer. Now we need to cancel out this root 3. V rated is getting cancelled, and you are left with the required term, that is I starting drawn by the supply in case of auto transformer would be X would be there, and you substitute this particular formula of I starting line by the machine root 3 times X V rated by ZSC. So it is X square, X into X. So the final starting current, let me just take some extra slides. Okay. Now let's write the final formula drawn by the supply. Your IST line current by the supply is equals to X square root 3. I got took out the X term outside and S square. So if you remember, this root 3 times the V-rated jealousy is nothing but the starting current in your DOL root 3 times V-rated jealousy. The same current we have got here, right? Now I can write this as X square times I starting of line in the DOL. So this is the starting current in the auto transformer. Now see, in each reactor based starting and also in the auto transformer starting, your starting current is being reduced. In reactor, if it goes down by the X factor, in auto transformer it is going down by the X square factor. We have reduced even more current in starting. Now let's see the starting torque, how much factor it is being reduced. Starting torque in the auto transformer would be 1 by 2 pi ns 3 times of starting current in the winding in the auto transformer whole square multiplied by R2 dash. Now 1 by 2 pi ns 3 times your starting winding drawn by the this would be x times V rated by ZSC. X times V rated by ZSC whole square R dash. Now, if you bring the x square term outside, the rest 1 by 2 pi ns 3 times v squared by zsc r dash will be exactly the starting torque in the direct online method. See if you see. This 1 by 2 pi ns 3 v squared by zsc r2 dash. So, x squared by t starting in the direct online. Now, if you see, I'm directly taking the ratio directly instead of taking the ratio individually like before. So your starting torque is going x squared and your starting current is going down x squared. So I'm just trying to write a summary here. In reactant starting, your starting current is going down x times, your starting torque is going down x squared times. And now in auto transformer starting, your starting current is also going down x squared times. Your starting torque is also going down x squared times. These both are very good methods. But the issue is in both of these starting methods, reactor and also auto transformer, we have to buy these components for ourselves. You have to get a three-phase reactor in that reactant starting method, and you have to get a three-phase auto transformer. Getting a three-phase auto transformer is very costly to buy, and you have to buy it and you have to put it between the supply and the motor, and then you reduce it and then they have to remove it once it starts, right? There's no role to play. It's like a very costly affair. That's why there is a another nice method, another which is a star delta method. No need to buy any components like reactor or auto transformer, but still you can get the reduced amount just by replacing the winding of your stator from delta to star. So you have to switch between this star delta starting. That's the reason for calling this method like that. So there comes the importance of the next method. See, only this method is only applicable if your motor is designed for a delta connected winding for normal operation. I mean, during normal operation, your winding should be in delta, because at the starting only we are making it as a star. Once it picks up, we will again switch it back to the delta. For normal operation, your machine motor is designed to be connected for a delta based winding only. So at the starting, designed, or you can say applicable, only for motor designed for delta connected stator during normal operation, not starting. So then what we can do at starting, connect stator winding in star, right? And then we will switch back. So we will see how that we will do. This is the winding of your machine in star at the starting. This is your rotor, cage rotor, and this is the star based star winding for your stator. Here you are applying the entire rated line to line voltage, and here you will have the starting current, that is line for star delta starting. Now if you try to calculate this I starting line, since it's a star connected winding, your line current would be equal to the phase current. So this particular phase current and this particular line current will be equal if it's a star connected. Now I starting in the line for star delta is equals to I starting winding in the star delta. Now what is this again? Here you are applying the phase voltage. Now can you tell me what is the phase voltage in a star connected system? Your line voltage and phase voltage will differ. Your phase voltage will be line voltage by root 3. Now your winding current would be phase voltage, which is rated line to line voltage by root 3 multiplied by divided by your impedance, that is 1 by ZSC. This is because this particular voltage is differing when it's a star connected winding. V rated, that's how you are getting a different kind of line voltage in the star this particular star delta. Now if you see this comparison with the DOL, it's root 3 times V rated by ZSC. Now but in the auto star delta you have V rated by root 3 ZSC. Now if you take the ratio of both I in the star delta divided by the DOL starting, you have root 3 in the denominator here, you have root 3 in the numerator here. It will be 1 by 3. And now if you see the torque, starting torque in the star delta is equals to 1 by 2 pi ns, 3 times of winding current, that is the phase current, whole square R2 dash. So it will be 1 by 2 pi ns, 3 times of, here will be applied phase voltage is line voltage by root 3 multiplied by ZSC, this whole square multiplied by R2 dash. See now if I bring the 3 outside and there is 2 pi ns, and I can, this 3 is 1 by root 3 square, I am taking it even outside, and V rated square by ZSC R2 dash. So this particular factor is nothing but the your starting torque in the DOL. So again it's a factor 3 by 1 by 3 times the starting torque in the DOL. Now your starting torque for star delta is equals to 1 by 3 times starting torque in the DOL. Now in star delta starting, a summary I am writing it here. If IST, your starting current is reducing by 1.3 and your starting torque is reducing also by a 1.3, 1 by 3. And if you see the auto transformer, if you remember the auto transformer factors, your IST is going down x square, your starting torque is also going down x square. So it's nothing, your star delta starting is equal to auto transformer when your tap ratio for your x is equals to 1 by root 3. for the auto transformer. So for in the auto transformer, you have this turns ratio, right? The secondary turns ratio. If you keep the x turns ratio in 1 by root 3, then your starting current and starting torque will be reduced by 1 by 3, which is same as the star delta starting. So you can achieve this auto transformer starting without even buying the auto transformer if you can make your winding a star connected winding in the starting, because we need that only for the starting, because for the normal operation you have to convert back into the delta and you have to improve your input voltage. At the normal operation, entire rated voltage needs to be applied for the windings. So that's how that's the significance of interchanging. So you have to change this winding from star to delta. So for that, you need to have your stator terminals available for you, and you need to once the machine rotates and its speed is set up, you have to change back to the delta based. So you might think that it's a very complex thing, but it's simple only. You just have to let's say this is the delta connected winding. You have this three phase winding A1, B1, C1. So delta is how what this is A2, B1, C1, B2, C2, and this is how delta connection is, right. And you have C2 will be connected back to A1, and you have this supply here A1, A2, B1, B2, and C2. Now this is the running operation you are expecting. Now initially you have a star connected. I'm not connecting it, but it's like a switch, right? Let me just draw even. So let's say you have your supply here. This is a supply, three-phase supply, and A, B, C you have. From this you have connected your three-phase. Okay. Now this is terminals available for you. Now A1, this is A2, this is C1, C2, B1, B2, and now you need to have a TPDT, triple pole double throw switch in this. You need three poles here, three poles ABC, triple pole, and double throw. Two kinds of junctions you need to have. Now I'm bringing down the terminals A2, B2, C2. I have three here, and this is the switch, and I have now these terminals are connected to, let's say, this one and this one and this one. Okay, now see A2, B2, C2 is connected. Now if I put this in this side, let's say you have two sides and you have another connection here. I would say this is B1 and this is C1 and this is A1. Now see, if you switch to the left side of it, it will connect it to this part and it will all be star connected. It will be star connected. Sorry. star connected at the starting. Now, if you connect the switch to the this side, now your A2 is connected to B1. You see this left side delta. A2 is connected to B1, B2 is connected to C1, C2 is connected to A1. So that's how I'm bringing this A2. This is B2. This is C2. Now A2 connected to B1, B2, C1, and C2, A1. If you turn your switch to the right side, it will be a delta connected. It is in starting and it is in the running condition. So that's how a small arrangement you need to make for the stator terminals of your machine, so that you will have a star based connection in the starting. The switch will be to the left side closed. It is star connection, and to the right side you will have a delta connection. It's just while the starting you will reduce the both current and the torque by a factor of 1 by 3. So that's the aim of doing such connection. Now we saw how all the methods can be implemented and what are the reduction terms in it. And now let's quickly look at the problems. We don't have much time, so we have only half an hour left. So let's quickly look into that. With this introduction, it is very easy to solve the problems now. Okay. Now the first problem says consider a 10 kilowatt four three phase 400 volts 50 hertz 4 pole slip ring induction motor. We are given a slip ring induction motor operating under rated conditions, and the motor torque occurs the maximum torque occurs at 16% slip, and it is double of the full load torque. Apart from that, stator impedances, core losses, and mechanical losses were asked to neglect, and we were asked to estimate the slip at the full load. So this is a kind of a lengthy problem, because we need to obtain slip at different torque conditions. But if you understand the concept and if you remember the formula, it will be easy to solve this particular problem. Let's see this. So we were given the Tmax at slip. So the maximum torque is occurring at slip is equals to 0.16, and we were also given it is double of the full load torque. Now the Tmax is equals to, so we have got some relation, 2 times the full load torque, and we were asked to neglect stator impedances, core loss, mechanical loss, everything is 0. Okay, now we were asked to find what is full load slip. Now let's go from the available data. We have the maximum slip, that is we used to call this maximum. S max is alpha, right? So we know alpha is 0.16. You also know the formula for it. R2 dash by Thevenin's RTH square XTH plus X2 dash. We derived it previous week, right? Now here we are asked to neglect the stator impedances. Stator impedances are what? R1, X1, and also since Thevenin's, if you neglect the parallel branch, you have, because they are asked to neglect the core loss also, so the parallel branch is not there, and the stator impedance, everything is neglected. Now R1 X1 are 0, R1 equal to 0, X1 equal to 0. So if R1 X1 are 0, RTH and XTH also 0. Okay, now if RTH and XTH are 0, you will be left with only X2 here. So R2 dash by X2 is equals to 0.16. So this is one relation you got from the given data. And another relation which we were given is the double the full load. Now let's see the formulas for individual full load torque as well as the maximum torque. Then let's see if we can get some relation. So we know the formula for full load torque, 3 VTH square by 2 pi ns. We derived this formula. You can just refer to the previous discussion if you don't remember it. It will be dependent on the rotor resistance, but maximum torque doesn't depend on the rotor. resistance, if you remember that. We'll also write the formula for maximum torque, xth plus x2 dash whole square. And the maximum torque formula is 3 vth square by, sorry, it's another 2 term will be there in the maximum, which will be 4 pi ns. And the numerator won't be there. It's not dependent on the rotor resistance. At the bottom, you will have the Thevenin's dependent terms. See, now if you substitute the Thevenin's terms zeros and all the neglecting the stator impedances and all, you will have TE full load. I'm substituting RTH 0, ZTH all the Thevenin's terms of 0. VTH will be input 3V1 square 2 pi ns. R2 dash by S will be there in the numerator, and in the numerator only R2 dash by S terms and the X2 dash will be there, right? And your maximum torque will be 3V1 square by 4 pi ns 1 by X2, because all the rest are Thevenin's only. This will be 0, this will be 0, this will be 0, and only X2 will be there. Now let's take a ratio of these two. Now we know the ratio is twice full load to the maximum is 1 by 2. Maximum is 2 times. We know that. Now, if you take the ratio of these two, 1 by 2, so this one will go on. This one, pi ns, but there will be a 2 factor in the numerator. Is it? No, no. It's already in the numerator. It will come up. 2 times here R2 dash by S divided by R2 dash by S whole square plus X2 dash whole square divided by 1 by X2. So this is what the ratio is, 2 times it. Now let's rearrange this problem things, and we will see what is a what arrangements we can make here. Let's see. So the ratio we know is 2 times, and we have 2 here, and I am bringing the bottom x2 to the top. We will have r2 dash multiplied by x2 dash divided by slip, and in the bottom you have r2 dash by s whole square plus x2 dash whole square. But from the relation 1, where the maximum slip, you know, r2 dash by x2 dash. So from this relation, what you can say, r2 dash is equals to alpha times x2 dash. So if here you can include this maximum alpha here, replacing it. So let's send this to this side, 1 by 4, and r2 dash multiplied by x2 dash divided by s. So if I replace this r2 dash with alpha times x2, we will have alpha times x2 dash square divided by, the reason I am doing is I am bringing everything into x2 dash term so that I can get the equation into one unknown, because rest everything I can calculate and I can get this x2 dash cancel somehow, and let's see what we will get. And in the bottom we have r2 dash. This is alpha x2 dash by x whole square plus x2 dash whole square. See, now all we have x2 dash square, we can cancel it, and you will be left with alpha squared by s divided by alpha squared by s square plus 1. Now if you simplify it, you will be left with alpha s, sorry, this is not alpha square, alpha s divided by alpha square plus s square. See, now you know the alpha, that is 0.16, you already given it the problem, and you have the slip. So this is, if you solve it, this is only the full load slip they are asking about, and this is a If you substitute alpha is equals to 0.16, you will be left with a quadratic equation. X squared minus 0.64s plus 0.0256 square, which is 0.16 square, is equals to 0. Now, if you solve this particular s, you will be left with 2. So yeah, we just have to solve this quadratic equation. If you solve these two, you will be having roots of the equation, which is the value of the slip full loads are two values. One is 0.597, another is 0.0429. So which is the valid value for this full load slip? Now, if you see the question, your the maximum torque occurs at S is equals to 0.16. Now, S should always be less than this particular slip, because for a stable operation of this, the slip full load slip would be less than the maximum slip at which your maximum torque occurs. Now, the value reasonable would be the 0.0429. This 0.59 is a not a valid value, so you have to pick it, and it is a 4.29% slip. Now, at this particular 4.29 slip, you will have the full load operation. So, you are asked to write this in the percentage form. So, it's a 4.29. So, it's simple problem only, but it's a bit of lengthy calculation only because you have to bring a good relation between the factors you were given and the data you were being provided, and that's how you can solve it. Simple only, but it's a bit of lengthy. Now quickly see the small problems they were asking. Speed at full load in RPM, that means NFL they're asking. If you know the synchronous speed and the full load slip, you can easily calculate it. We just calculated full load, and to get the NS, you need 120 F by P into 1 minus S. So it's a 50 hertz machine and a 4-pole machine. 4 into 1 minus 0.0429. So it's 1000 into 1 minus 0.0429, it will be 1435.69 RPM. What is simple only, just calculating full load speed. And its maximum torque. So, what is the formula for maximum torque? So, maximum torque is nothing but your shaft output, right? That is the, shaft output is the full load torque. You are asked the maximum torque. It's the fourth one. Okay. There is another problem here which I want to also discuss. Is the full load torque in Newton meter. So to calculate the full load torque, it is the shaft output torque. So if you know the air gap power, you can easily calculate it. But usually the formula we know is PAG by 2 pi ns. But if you don't know this air gap power, you can also calculate this P output gross mechanical divided by 2 pi nr. That also a formula, because you know the P output. It's a 10 kilowatt machine in the problem. So 10 kilowatt divided by 2 pi, and nr, small nr will be capital Nr by 60. So capital Nr we calculated already, that is 1435.69. This is RPM, you need to convert it into RPS. So this is your full load torque. If you calculate it, it will be around 66.3 Newton meter. This is a full load torque. It's easy if you get the value. Now it's a maximum torque you are asked. So you can go with the formula, but in the data, in the question itself, it was given your T max is 2 times the full load torque. So you already calculated your full load torque, that is 66.5 Newton meter. So the 2 times will be 133 Newton meter. And it's a starting torque. Okay. Now starting torque is nothing but the torque at which your slip is 1. Now, if you know the relation between the maximum torque, full load torque, you can easily calculate it because you don't know any parameter to calculate torque actual values. Now, you know the full load torque and you know the maximum torque, and you have to somehow calculate the relation. See, from the first problem, when we took the ratio of it, you have full load torque to the maximum torque. You have got some equation like 2s alpha by alpha square plus s square. So this s related to the full load and this alpha is related to the maximum torque at which your occurs. Now if I want to rearrange this in terms of starting condition, I will keep the maximum itself. So at the starting condition s will be 1. So 2 times alpha multiplied by 1 divided by alpha square plus 1 square. So it is 2 alpha by 1 plus alpha square. So in this you know the maximum. You know alpha which is 0.16 and you can easily calculate the starting torque is equals to T maximum multiplied by 2 times 0.16 divided by 1 plus 0.16 square. It's very important to remember the conditions and the relations which you have from the problem. So that's only the key for this problem. Once you get the relation, there is nothing, it's just substitution of it. So the maximum torque is 133 multiplied by this entire term. You will give the 130 times this one. This will come out to be around 41.5 Newton meter. That is the starting torque. Okay. And the key to this problem is to get this particular relation. So how did you remember? Because you already know the full load torque by maximum torque ratio, which is slip dependent. Or if you the slip substitute s is equals to 1, that is at the starting torque. So you can replace this full load torque term with the starting torque. Okay, now the next problem is to calculate the rotor copper losses. Okay, all the other losses were given to be excluded, but rotor copper losses we can't exclude because the current is flowing. Now, one such relation we already derived in the previous class. Rotor copper losses and air gap and also gross mechanical, we have this relation 1 is to S is to S1 minus S, right? So this rotor copper losses is equals to S times the air gap power. But still we don't know the air gap power. So let's get the relation between gross mechanical that we know the output rating of the motor. That is air gap power into 1 minus S. Now I need this rotor copper losses. That is what I will calculate. Rotor copper losses is equals to S times of PAG. Instead of PAG, I can substitute this P gross mechanical divided by 1 minus S. So it's simple. Now you know the at full load. So all are at full load and S is full load, S is full load, and gross mechanical you know the output. It's S full load is how much we calculated for 4.29%. 1 minus 0.0429 into gross, that is 10 kilowatt motor. This one. So you calculate it and you solve it, you will get around 450 watts. This is the rotor copper losses you can have at the full load. And now we are asking about the ratio of starting current to the full load current. Okay, it's simple. Like if you know the ratios of torques, it's just substituting it. Torque is nothing but 3I square R divided by 2 pi n. That's a constant. Now if you see starting torque divided by full load torque, if you have this ratio, it is 3 times I starting square divided by R2 dash by S, which is 1 in the starting. So there will be a 2 pi ns also. 2 pi ns, this will cancel. So it will be 3 IFL square multiplied by R2 by SFL. Now, this is the full load slip and this is 1. Constant constants will get cancelled, and 3 will get cancelled, and you know the starting torque and also the full load torque. Starting torque is 41.5 we got, and full load torque 66.5 we got, is equals to IST whole square divided by IFL whole square multiplied by R2 will get cancelled, and your full load slip. Full load slip, we calculated it's around 0.0429. So you need this particular ratio. So you can send that ratio to the left hand side, is equals to 41.5 divided by 66.5 multiplied by 0.0429 under root. So if you calculate this, the ratio will come out around 3.815. So this is the ratio of starting current to the full load current. It's just getting all the relations you have to once you get the um, formula right. So that's the key. Okay, another relation. This is the last relation we will see for today. So current at the maximum torque divided by the full load torque. So current at maximum torque. So the I at T max divided by the IFL. Again, go with the torques because we have the values of all the torques available with us. Now I will go with the maximum torque formula divided by full load torque formula. So the maximum torque, it's I at T max square multiplied by R2 by 0.16, and there will be divided by the factor full load current square multiplied by this R2 dash by S. But S is important. You will have the maximum slips. So this I at T max square multiplied by R2 by S. Here S is the slip at which maximum torque occurs, 0.16, and the full load current square multiplied by R2 divided by the full load slip, 0.0429. From the data of the question, you know this maximum torque to the full load torque is twice the data you have given. Now 2 is equals to required current at Tmax divided by IFL square multiplied by 0.0429 divided by 0.16. So this is what you require, and the required ratio, the I at Tmax divided by IFL is equals to 2 times 0.16 divided by 0.0429 under root. So if you calculate it, you will get the factor ratio around 2.73. Also, you go with the torque formula, you see you have values, or you can go with the data which was given that we see maximum torque is twice the full load torque, and you can substitute and get the answer. So the last question for today is the full load efficiency. Efficiency full load is always equals to the output powered by the input power. Output, you know, it's a 10 kilowatt machine, but input you don't know. The other way to calculate the input would be output by input plus losses. Sorry, output plus losses. Even though it was given to neglect all the stator impedances, core losses, and the mechanical losses, but we calculated the rotor copper losses that you can add to the output to get the total input. So the rotor we got around 448.2 watts. So it's a 10 kilowatt motor multiplied by 10 kilowatt plus 448.2. Now if you calculate the ratio, it will be 95.7% efficiency. So it's again simple output by input. So since you don't know the input, it was not given, you can calculate the input by adding the output to the losses. So this is what we are going to discuss today. So here we will be ending our discussion. But let's have a quick discussion with the concepts we have discussed today. We started our discussion with a very important concept, that is the starting of three-phase induction motor, and why the starting of induction motor is important to understand. Because at the starting, the machine starts with the inertia, and it needs to overcome that inertia in order to start it. And we have seen the importance of understanding the starting, and to overcome it, it will draw a large current. That also we saw. And at the starting, the conditions and what happens, how it is drawing that much more current, we started with that. And we saw at what conditions it is okay to pass it, whether it's a small motor or big motor, based on the inertia of the machine and the time duration for which the current is passing. We saw that. And then we saw the starting uh, troubles, issues at the source side as well as the motor side, and that established the need for going for the starting method. And we discussed the two different starting methods, that is direct online starting and reduced voltage starting. Reduced voltage have three different kinds: reactor starting, auto transformer, and the star delta. We discussed the individual methods, and we estimated the starting current as well as the starting torque, and compared it with the standard DOL and all the reactor starting and auto transformer and the star delta. So we got the ratios of each and every case, and we saw how the starting current has been reduced, and even starting torque is getting reduced because of these methods. And then we proceeded for the problems. We solved all the important relations. We all these relations we discussed in the last week, so it should not be a much problem. So that's it. So the key is to remember this formula is good, and you have to quick think and how to get a relation between any two factors if they're asking something. So that's it. If you have any doubts, you can ask right now. Even if you got any ideas, or if you during the week, if you have any doubts regarding the lectures, you can just raise the queries in the discussion forums. We will surely get back to you on that, and we will pick up your discussion threads in the comments, or we can directly discuss in the live sessions. And I request everyone to actively participate in the interaction sessions of this, because you will get the opportunity to put your doubts directly to us, which we can directly discuss back to you. Okay, if there are no doubts, we will end our session for today here. And I request everyone to practice these problems and submit your assignments on time. And we will discuss the forthcoming concepts in the coming weeks. And I thank you everyone for being patient and listening to me for the last couple of hours. And thank you all. We will meet in the next week, Tuesday, 6 to 8. Thank you.